Welcome to Unapologetically Technical. My name is Jesse Anderson. This is the show that's different. It is unapologetically technical because we go deep. We go all the way down. We go into the deep technical parts, into the deepest recesses and deepest, darkest recesses of the various technologies. In this case, we're going to be talking about Spark and how we can do real-time Spark, and we're going to go deep into that. With me today is Karthik Ramasamy. He's the head of streaming at Databricks. Welcome, Karthik. Would you mind introducing yourself a bit more?
Thanks, Jesse, for the opportunity to come on to your show. It has been a pleasure. So to give a brief introduction about myself, I'm currently the head of streaming at Databricks. It has been close to 2 years since I joined Databricks. Before joining Databricks, I was at Splunk managing their streaming product. And before Splunk, I was running my own business called Streamlio that got acquired by Splunk. That's the way I ended up at Splunk. Before starting Streamlio, which is the company that I founded, I was at Twitter managing the real-time processing engines, namely Twitter Heron and Twitter Storm. I came to Twitter through an acquisition of my company again called Locomatics. That's how I ended up at Twitter. So before founding Locomatics, I dabbled into networking and other aspects of system building. And before joining Juniper, I finished my PhD at the University of Wisconsin-Madison with a focus on large data. Today we call this big data. At the time, we were calling it sharded and large data. So that is a brief introduction about myself, Jesse.
Well, welcome. I'm really excited about this one because one, I've known you for a long time, and two, you have this deep technical background that is really hard to come by, having been doing this for so long and at such large scale. So tell me, what makes you so interested in, you were talking about large data and sharded data. What made you interested even then?
Well, it's funny that how I ended up here. Actually, it's a long story. When I was starting my undergrad program in computer science, on the fourth year of my undergrad, we had a database course. So at the time, we were studying the date books. If you remember the CJ date books, which is one of the decorated authors of a lot of database books, right? So we were reading about how database modeling happens and SQL and all the various other aspects of database. I mean, to some extent, like largely the peripheral aspects of database. And I found that what is this? This is too easy. It's kind of boring in the sense you just have SQL, it gives answers and all. What is so fun about it, right? It does not involve real systems work, right? Then I came to grad school in the US. Then I studied the advanced database system. Then I realized how hard it gets as you go down deeper into the internals of database system. That's what got excited me into the database field. So then I went to University of Wisconsin when I did my PhD. I went there with a specific focus on doing a PhD in databases. And I'm glad I got the opportunity to go there because it's one of the best programs in the data world that the researchers that has been produced have gone on to staff at power a lot of database systems that are very commercial out there, including Microsoft SQL Server, Informix, IBM Almaden Research Center, a lot of people at Google, and some of the popular open source projects as RocksDB, Hive, Heron, and a bunch of these things have been started by some ex-Wisconsin folks. So it has been a very good ride, actually. In fact, at Wisconsin, we worked on large database systems. So at the time, we were doing a 100-node MPP system, which is unheard of, during 96, 97. The only system that bigger than whatever we were doing was up in Walmart, which was doing 300-node system for their Teradata deployment. So it has been I've been very fortunate to work on those kind of systems that helped me exposed into this big wealth of or big area of large data processing or MPP systems at the time.
But what was it that made it? What made it University of Wisconsin so nice during the 90s? Because I told you that our last guest, graduated from University of Wisconsin Madison too. Was there a professor? Was there a grant? What was it?
It was a combination of both. We had great professors like David, Jeff Norton, Michael Carey, Raghu, Yanis. So like 5 faculties who were doing large database systems, and they were all topmost in their fields, right? But the credit goes to David, who started this program in 1977 after he graduated and came to Wisconsin. He was dabbling with database machines, like the hardware for databases, because he had an architecture background. Then as he was doing all the database machines kind of research, then it kind of dawned upon him how software and the sharding of the data will go a long way to processing large amount of data. Then they built the database faculty. Then Mike Carey was hired, then Jeff Norton was hired, Raghu was hired, and Yanis was hired. So like all the faculties were doing so much database system. In fact, like we used to publish so much research out of Wisconsin. Like we had an acceptance rate of 50% to 60% in VLDB and Sigma, the premier database conferences. So that was one. Second one is like there was a program in NASA at that point in time where NASA was launching a bunch of satellites and they were photographing the Earth every few minutes or whatever, and they were sending all the data. And that data was envisioned to be petabytes of database, petabytes worth of data. And they needed a system to process that much amount of data. And in the early 90s, we didn't have such systems at all. So the research project was given to Wisconsin and a few other universities. Then people came up with the idea of sharding the data, storing the data in fragments in for each machine separately, and what we call as today as a shared nothing architecture. And then how to do the processing of those queries, how to on the sharded data, right? So that jump started all the MPP style systems, and so the Wisconsin made a specialty in that the processing large data. And even though when we graduated, the large data was not it's a domain of a very few companies, but with the explosion of all the internet companies like Google, Facebook, the data became so big, and the importance of data has grown so big because of the analytics and other things that you can insights that you can drive out of it. That made the data processing field as a big field into the whole IT the software ecosystem. In fact, like a lot of my friends went on to become faculty at CMU, Cornell, then Berkeley, Stanford, um, uh, Singapore universities. Some of them ended up in Waterloo, and some of them ended up in AT&T Bell Labs, Almaden Research Center, SQL Server, Oracle. So the program graduated around 400 graduates, 400 plus graduates over the period of this thing. We had last time we had a 40th year reunion of our program a few years ago. Hopefully, we'll do the 50th year anniversary of the University of Wisconsin database program.
It sounds like
That's what's special about it.
you need to. Yes, yeah. Yeah, and all the time I've known you, I didn't realize I knew you had your master's. I didn't realize you had your doctorate. But you mentioned Michael a few minutes ago. Was that Michael Stonebreaker?
No, Michael Carey. He was the Michael Stonebreaker student at Berkeley, and he graduated, and he joined. David recruited him to join at the University of Wisconsin-Madison.
Okay.
Yeah. So my advisor is Jeff Norton.
So what advice would you give somebody who's trying to, sometimes people are trying to make a choice of going into an academic or finding the right university? What would you tell them to do?
I think if you wanted to do a database or a data related programs, I think all the top universities are good choices. Berkeley, CMU, Madison, Stanford, even MIT has a good data program at this point, but it's more focused on AI. So all the good schools are there actually. So now the choice is whether you wanted to go academia or you wanted to go research labs in the companies, or you wanted to do build products. So my take was that even though I'm building products, I find that doing a PhD was very helpful in looking at the problem in a different way and systematically tackling it. What PhD teaches you is abstract the problem, simplify it, solve it, and expand it. And so that kind of methodology helps you to tackle the product problems as well. That's what I found it very useful.
Okay, well, let's move on to your time at Twitter. So for people's context, there was Storm and there was Huron. And my recollection of that story about Storm was there was a project and that Storm actually bought that company in order to have to develop Storm, and you were brought on later to create Huron. Is that correct?
It was actually a little bit different. I mean, the first story was true. The Twitter bought Backtype, which was processing a lot of real-time data, and that's where the Storm was originally invented. And Twitter bought Backtype and deployed Storm to process the Twitter data. In the case of for several applications internally, like art targeting, spam detections, and a bunch of things like that, right? So the Storm grew into 3,000 plus machines at Twitter when I came in. So now our charter was to fix Storm in the sense like it was cracking up as a scale because it was never done for a lot of scale. The Twitter scale is beyond the imagination of original Storm. So that scale, at that scale, some of the problems started showing up in the sense like there was a problem with Nimbus, which was not scaling up to serve a lot of metrics for large jobs, and the executors and everything was interacting in a very complex way when multiple jobs were running in together because there was no isolation and other capabilities. So each was influencing the other actually. Then it was never had a proper, even though it had a scheduler, not a cleaner integration into orchestration systems like Mesos and Kubernetes and those kind of systems, right? So then we had other issues like GCs and a bunch of things like that. When you looked at it, like there are two choices. One is to rewrite Storm and or do a new system or fix the existing system. And a team evaluated all the various pros and cons, and they recommended rewriting a system into a new system, but with the API compatibility, right? So that's when Twitter Heron was born. Twitter Heron tried to solve all the problems that faced with Storm right from the get-go. Like isolation was done at various levels, like at the individual operator level, at the container level, at the job level, various kind of isolation that we ended up doing it. And it's also cleanly was able to orchestrate with off-the-shelf schedules like Mesos and Kubernetes. and also like observability. When the Storm jobs are running, or Heron jobs are running 24/7, one of the key things that you figure out, you have to fix the issue that comes with that very quickly. And that was translated into a lot of metrics. And even we put some kind of a rule-based system that allowed it to capture the metrics and automate what are the problems that are occurring in those rules that can trigger some popped up the issues proactively so that you can go and check the issue before even it pops up. So the Twitter Heron was eventually open sourced, and it's out there. It's an Apache project, but not a lot of traction since people have moved on from the Storm API to build a higher level of abstractions like Spark and Flink and KSQL and a bunch of other systems started coming on through. So that's I think when I left Twitter, the era of streaming systems was starting, but more focus was on the ease of developer experience rather than the system actual aspect of it.
Much to our chagrin, because now we have some systems out there that weren't really thought of, and now they're trying to do the other side. They're trying to take these ease of use systems and put the hardcore engineering into them, which doesn't really work. The other way works.
Yes.
So I think the industry is about to make a few unhappy or difficult realizations. Let's just put it that nicely. So speaking of that,
I think expanding on that point, these two things are different beasts. Scaling the system is a different beast versus having a developer experience is a different beast, because it requires two different talent. You need talent. Unless both the talent comes together, then you can make the system work on these two different dimensions.
Yeah. So speaking of those lessons, what do you think the other lessons of Storm and Huron were?
Another thing I learned is managing a good team. Because we had a lot of talented people in the team, and all they need is some kind of vision and some kind of boundaries to play around with. And they were very happy to, in fact, the team delivered within 9 months. So a system from ground up to getting it into production. So within a year and a quarter, we migrated everything and this thing. So that is the speed at which we worked. So that is a very good lesson that we learned of managing a good team, actually. And the second theme is thing that we learned in the system is scaling systems is hard. You have to think about scaling upfront, because scaling hits it at the parts of the system where you never even think about this thing. For example, simple socket-related aspects, right? How do you connect a socket connection and keep the socket connection alive and multiplex into that one single socket connection, as compared to opening sockets for every combination, because it explodes the sockets, as compared to having one socket and multiplexing data into that, right? And the problems around with it. So these kind of even smaller issues can blow up the scaling aspects very quickly. So that is another aspect that I learned the hard way. And it got a lot. And another thing is, when people use the system, they need to use it very effectively. In the sense they need to get the job done quickly once they understand the system. So which means the manageability and operability of the system is equally important compared to the developer aspect of the system as well. So that's where because when the system is running in production and something goes haywire, we need to get the system back up quickly. So because a lot of downtime dollars are involved, right? So in order to avoid reduce the downtime, it's very important that we have a focus on observability and ability to proactively pinpoint the problem as compared to reactively. We need to have a reactive component as well because sometimes unexpected problems occur. So, but the thing is, you need to resolve it quickly. So that is another hard thing that I learned.
And one thing there were two things I found interesting in that. So I dug around and I talked to a few people there at Twitter, because sometimes there's what Karthik says and then there's the reality. No offense, Karthik. So I asked people just how easy was this cutover, because I was completely surprised that a cutover of this magnitude, where you were doing API compatibility like that, was that successful. It completely surprised me. So good for you. Congratulations on that. And the other thing that's I'm sorry, go ahead.
Yeah, that is the API compatibility is the key thing, because if you ask them to rewrite the program, your migration is going to be hard, because the other teams have to be allocate some time to migrate and rewrite the programs. And usually it's very hard in enterprise kind of environment to rewrite the programs, because that requires more developer time, debugging time, and testing time before it goes into production, right? So on the other hand, if you do a migration, which is just to do a recompile and relaunch, that's what we call them. The recompile and relaunch, and we guarantee everything works. And once it is done, then we help you optimize it so that you can reduce the cost. Because Heron was 5x to 10x faster than Storm, so we can optimize all the resources, right? So that's the way we launched. And ultimately, when we tallied up all the cost savings that we got, we saved around close to $10 million.
Well, good. Yeah, that was around that time was when we first met. I think when you had either first released, or yeah, I think it was around that time, or perhaps shortly after that. Okay.
Yep. I think we met at Twitter when we were having a meetup or something like that. I think you showed up there, and that's where we met first, actually.
Yeah, that was. I got to go see the log cabin and all that fun stuff. So
yes. Those fun times that too.
Yeah, I remember it fondly. I one thing I've been thinking about lately of that I think people will like, or as you hit these times, know that these times are going to be unique in your life, and really enjoy them and savor them, because the next time may be good in a different way, but it won't be like that one. And that was a fun time.
Yeah, it was indeed a fun time. I enjoyed every bit of Twitter.
So you mentioned just briefly about management. What do you think the marks of a good manager is? A good engineering manager, I should say.
Yeah, I think like exploiting, trying to bubble up bottoms up ideas is a key aspect of a manager. Second one is draw the boundaries. Draw the boundaries. Within the boundaries, you can make the team very creative, and so that employees are happy. At the same time, we work for the overall goal of maximize the company's shareholders' value, right? That is the second thing that I learned. Third thing that I learned is constant juggling act that we have to do, right? Request for features, request for um, uh, teams' healthiness, and teams willing to do something interesting. So we need to balance all these acts together to keep all the stakeholders happy. That is the challenge engineering manager has to manage, so that the team is creative enough to come up with the new ideas, at the same time creating new systems or make the existing systems better. At the same time, it benefits the company. So these are the aspects of a engineering manager that you need to balance around to be a good engineering manager. You have to manage upper management as well as lower employees and manage your peers.
This whole management thing will come full circle because when we start talking about Databricks, when I first heard that Databricks had hired you, and I was talking to your new boss, and I said, "Wow, you really scored the right person, the perfect person," because not only did he have this incredible management pedigree, this incredible education degree pedigree, but had also done it before. So they found just the exactly right person to start working on structured streaming and improving that. But we'll talk about that later, and we'll get deeply into that.
Okay.
But in between, so Twitter open sourced Huron, and you left Twitter and you started Streamlio, and that was your second business. What did you learn that second time around?
So like our thesis was like when the Twitter Heron was open source, Storm had a decent market, like 100 plus customers were using, potential customers were using it. Then we came up with the Heron. We thought we will take that Heron and get into the streaming side of things, right? And make the enterprises do streaming so that they can also benefit what Twitter benefited. So that was the thesis. But one of the challenges that we faced was we were a little bit early, in the sense like streaming was more of a technology for a lot of people, a curious technology, a lot of people, rather than a pain point. I mean, usually startups try to address a pain point and grow over it. Rather, we are doing something for the need for a feature, not right away pain point, right? That is the first one. So, so instead of dealing with the Heron, then we pivoted into more into messaging / queuing kind of systems like Apache Pulsar. So we our initial vision was to deliver an end-to-end streaming system, including messaging system as well as a processing system as well as what do you call storage system. Combine it together in a tightly coupled way to do a end-to-end streaming system. So then as we realized that streaming is too early, we focused on the messaging side of things. And Pulsar was a great technology that we had, having recruited a creator of Pulsar called Matteo. So it was a good product and a good open source. Now the challenge with Pulsar was it was the start of the journey of Pulsar. I mean, we evangelized Pulsar, brought Pulsar to the forefront by constantly talking about Pulsar and its advantages. And so the enterprises are just starting their head towards concentrating on Pulsar. But in order to make a viable business quickly, you need to have a lot of adoption. As adoption takes 5 years to go beyond a certain threshold. So on the other hand, like startups don't have a 5-year leeway, right? To just do adoption, we have to kick in revenue. So that's why, like, when you start an open source business, make sure that your software is completely widespread adoption before you can start a business. So you need a 5-year cap, 5 or 6 year cap before you start, or you need to have a runway for the 5-6 years to just do only adoption. So that is a major things that we learned at Streamlio. So luckily, like we got an exit at Splunk where they wanted the technology and they wanted the expertise, and we had a nice exit.
Yeah, we'll talk about that in just a second. So you were talking about Pulsar. What's your feeling on Pulsar right now?
Pulsar is growing decently, very well, in fact. I mean, last I heard is some of the bigger companies like Flipkart and companies like Tencent and other folks have adopted Pulsar, and the ecosystem is growing. And in fact, there is a lot of ask for Pulsar connectors as well. So that has been in the works, and we are also um, adding Pulsar connector as into the Databricks runtime for launch. So because the companies have been asking for a Pulsar connector as well, like native support for Pulsar connector. So so Pulsar is growing. It's a, and I think the landing point for Pulsar happened to be not messaging, but however it landed up in the queuing side of things, like a better Rabbit MQ or better AMPQ, right? And expanding on to the messaging side rather than landing on the message side.
And to help people understand the difference between queuing and messaging, unless they're not understanding that, is queuing is when you're putting a message on that needs work done on it. So you need that to be here. Let's put a message on. A piece of work needs to be done. That isn't something Kafka does remotely well. It's just not. Though they're adding it, I'm curious how well it's going to be added. I think this is an issue that we kind of alluded to before, of when you take a technology that's made for this and then you try to add this, and this, how well it does in those other things is probably not going to be as well. For example, I'm really curious on the Kaplan improvement, if they actually are going to make server-side improvements or they're going to try to do this client-side. Have you looked at that at all? I'm curious.
No, I've not looked at it for a while. In fact, I moved on from the world. Now my focus is on Spark structure streaming. So
yes, well, we're talking to the right person about that. I'm going to have to find out more about that. So you talked about that acquisition at Splunk. So when you and I were talking one time, where you were back to scale again, you were dealing with such huge scale where systems that were known to scale pretty well were actually breaking. What did you learn as you were debugging that?
yeah, it was a lot of learning at that point because that Splunk scale was unprecedented. We had a large financial customer pumping around 120 um, gigabytes per second. That's a lot of data that we need to process, actually. And so the option was to have a big pipeline that can process that much data, but none of the systems that we talked to had that much scale at that point in time. So, in fact, the DSP, that product that I was using, it was using Pulsar, Flink, and Splunk, and none of the system has been deployed at that scale for processing that 120 gigabytes. So then we scratched our head around and tried to figure out what we can do. So we ended up going on a little bit complex side of things, where we ended up sharding the data based on some business units or whatever it is. So then, which means that 120 gigabytes of data is sharded into X 20 gigabytes for one set of pipeline. So like divided into 6 or 8 different pipelines, so that each one can handle around 5 to 10 gigabytes per second, right? So the smaller pipeline, because otherwise, since 120 gigabytes is a steady state, and during holiday time and Christmas time, the transaction is going to go much higher, right? So that way, like individual, by sharding the data into smaller pieces and associating 5 pipelines per shard, we made the each shard scalable, and they have room for growth as well. So, but the downside of that is you have to manage so many pipelines, right? So there were 3 or 4 use cases and the around 10 or 15 pipelines each, that became to 45 pipelines, right? So instead of 3 or 4 pipelines that you have to manage at the scale, we ended up having 45 to 50 pipelines to manage that and the corresponding resources and all the various things like that, right? The second aspect that we learned is at the scale, one of the major considerations is cost. Because already you're processing so much data, you're spending so much cost on that whole thing, right? Instead, the customer indicated that you need to reduce the cost, right? When your cost becomes an issue, when you try to optimize it, you try to find out a lot of inefficiencies and everything, the code as well as the cloud provider, what are the things that we can exploit. So it was a very hard challenge. So the lesson that we learned is in the curve of the SLAs of cost, throughput, latency, and accuracy, usually cost trumps everything pretty much.
Yes, cost will inevitably become. We can either cost 100 million or it can cost 10 million. Which do you choose? And generally, people will choose that 10 million.
Yes. Mm-hmm.
Okay, so that was an interesting way. I never did hear the end of that story before. So okay, so you sharded it, and you talked about one of the issues that you had of you sharded it based on business unit. Did you ever have to do a join across business units, or was that not necessarily?
It was not that. That is the first thing that we asked for, whether you want to correlate the data across business units, and they didn't have anything that led to sharding the data. So otherwise, we would have, sharding per use case, right? So that was a challenge. In fact, like we tried other approaches like what do you call single pipeline approach, right? And we also try to push the scaling around. But thing is, like the systems are not designed to scale unless it's and we were we didn't make the choice of the system when we went in. The choice of systems were already made. So the only choice that we had is cut over from Kafka to Pulsar. Pulsar scaled very well, but Flink and other things had a limitation of 5 to 10 gigabytes per second because that's the way they operated on. So that's why we had to work with the threshold that the systems have been tried before rather than trying to stretch the system much beyond that.
Okay.
Because you never know what kind of issues are going to occur, right?
No, that's part of why you get a PhD and why you get paid the big bucks. Is you need smart people around to figure out these issues. So speaking of big bucks and getting paid, Databricks, your current company, and currently where you're focused at. So what we're going to do is we will switch over and start doing some whiteboarding now. So the first question I have for you is, what is Spark Structured Streaming? And if you could whiteboard out that for us, please.
Yeah, Spark Structured Streaming. So initially, Spark Streaming used to be what you call as I don't remember that. So currently we have the data flow API, which is the Spark structured streaming. Spark streaming is data as RDD API. So that was the first version of Spark streaming, which uses RDD API. But Spark structured streaming uses a data frame API or data I think it's data frame, not data flow. So data frame API. And data frame API is the recommended version of Spark's streaming usage. And the data frame API builds on what you call Spark SQL engine. So like a Spark SQL engine is, and on top of which we can specify Scala API, Python API, and SQL API. So this SQL engine, do you want me to go into detail into how the SQL engine takes data from query and go into the details?
Sure.
Okay. So you have a data frame query. Then this data frame query is converted into a logical plan. Then the logical plan is fed into some kind of analyzer. And it spits out a analyzed logical plan. Okay. Now, you must have heard about the fact that Fox structured streaming is a microbatch. Essentially, what it means is the data is divided into, if you have a stream of data continuously coming in, that's divided into smaller batches, like B1, B2, B3, B4, B5, and so on. And for each batch, we run a query. Query 1, query 2, query 3.
So just to be clear here, time is going this way. Time is
yes.
Time is incremental.
Time is incremental this way, right? So like now the what I talked earlier about having a data frame query converting to logical plan and goes to analyzer, converts into analyzed logical plan. This is done once. Now, there's a second part which does for every batch. So for batch 1, you take the analyzed logical plan, then feed through the optimizer. Then you get an optimized logical plan. Then you go through a planner. Then spit out a Spark plan. So this Spark plan gets executed physically.
So a quick question. So you just said that this piece right here is done on every time. Why are you doing analysis every time? Why wouldn't this just stay the same each time?
So there are advantages, disadvantages as well. I mean, the advantage is, for example, when you're running a query for a particular batch, and when you detect using statistics that the data distribution has changed, right? Then you can re-optimize it.
So for data skew.
Go to the next batch, you can do the re-optimize depending upon the statistics, which we call as the adaptive query execution, right? So that is the advantage out of this one. But one of the ideas that I'm thinking about is whether to re-optimize it only when it's needed. So look at some flag, hey, re-optimize it because I've seen some statistics different, then re-optimize it, otherwise skip the step, right? So I think like when you first implemented this one, when the originally Spark structure streaming was implemented, because of the simplicity it offers, because remember the code path that you goes through is same as the batch code path, right? So this makes it much easier to keep the code base the same and execute the queries again and again, whether independent of whether it's a Spark structure streaming or a batch query, right? So that's the beauty of this engine. So now as we make more optimizations and reduce some of the SLAs or like latency improvement, some of these things could be optimized. So this is batch one. So same thing gets executed for batch two. So batch two again. We analyzed logical plan, then goes through optimizer, then optimized logical plan, then planner, Spark plan. So this is for batch two. So it keeps repeating the same thing again and again. And so there are different trigger modes that are available. One is the default is continuous mode in the sense like once batch one finishes, batch two starts, and batch two finishes, batch three starts, keep going, right? Then we can do incremental processing called available now. So the Spark job will start and take all the data that is available, finish it up, and go on a periodic fashion too, rather than continuous. So that way, like you can do a incremental as well. So depending upon when the triggers it, right? So that way, it's very flexible. You can go to batch, you can go to incremental, you can do continuous. There are three spectrums, right? So with Spark, you can do batch, where you process data only once, right? Incremental, available data now. And continuous. Keep processing. So that way, like all three different modes are possible with Spark.
And that's kind of the holy grail that we want in the industry is we want a single processing system that can do batch, can do incremental and continuous processing.
Yes.
Yes. I've seen desire for incremental, but the true one is this batch and continuous. So
yes,
when I talk about Spark, probably let's rewind, let's say 2 years. Spark had a great batch, but not as great continuous. And then we compare that with something like Flink, where it had a great continuous, but not a very good batch. And so you had to make a choice of, do I want good batch or do I want continuous? So what's happening in our industry is we want one processing system to rule them all. And the company that does that will do really well.
Yep. So that is a good observation. Definitely, like Spark originally started from the batch world, and but one realization that I have come to in mind is having done continuous processing systems like Twitter, Storm, and Heron, and worked with Flink. Initially, like when I looked at Microbatch from the eye of a continuous processing system, that said like how batch will be behaving, what kind of issues and other things will happen and all. But the thing is, now coming into Spark Microbatch world, uh, I see the benefits that not many people see actually in the Microbatch world, right? So it's an elegant architecture in the sense like it slices going from batch to continuous and continuous back to incremental, back to batch, right? Um, so the application is of the scenarios in which it can work is humongous. That is one advantage of Microbatch. Second one is Microbatch offers opportunities to do a re-optimization, replanning, and everything at every Microbatch. For example, auto scaling event can come on at the batch boundaries, right? And state flushing and can occur at the batch boundaries, right? So these are all operations that you can do on a batch boundaries that you can clearly and seamlessly do it. And also, when you fail over, you don't have to reprocess a lot of data. You can go to the last batch, checkpointing, and replay from that, right? So, so that way, it is a beautiful system, actually.
Yeah, I remember having more of those conversations where, yeah, it was interesting to think of Microbatch and some of the benefits it gave, and not just in terms of what the latency issues were. So one point that we didn't make in that previous discussion was so during this Microbatch time frame of, let's say, batch 0, there's a certain amount of time that is taking place here, and depending on which version of Spark you were using and how long ago, this could be anywhere from seconds to hundreds of milliseconds. So there is some amount of time, somewhere between seconds to milliseconds, that goes by here and waits for that batch to fill up.
Yes. So actually, in a batch itself, there are multiple things. If you look at, if you have a batch, there are some metadata operations that happen in the front of the microbatch. Then processing happens, and some metadata operations happen in the second part of the microbatch, the end of the microbatch. Okay. So start, end. So what we have done is we have optimized some of those aspects to reduce the latency. And in addition to that, there are the metadata operations can involve scheduling too. I think I need to, before I go into all these things, I'll go into the how the microbatch physical plan or executes before I talk about this to detail. But the key thing to look at is there are metadata operations at the start of the batch, end of the microbatch, which can be optimized to reduce the latency. This thing, the task execution time can vary depending upon what the logic is, right? That is what the processing logic is. Processing logic can be very heavy. For example, if you are running your own algorithm inside it, it can be very heavy, or it could be very simple, like simple transformations that you might end up doing in this, in which case it will be pretty fast.
So to put that in a different way, so your microbatch, let's say, could be 500, let's just make it 500 milliseconds. Your processing time could take 100 milliseconds because it's pretty lightweight. Or in a worst case, you're actually exceeding your microbatch and doing that over 600 milliseconds. And that was often when I saw people trying to increase this processing time to account for this. So oftentimes they were trying to do way too much in in their processing and should have done it either a different way or
Yes.
optimize
So if
something.
you're, especially if you have your own own code that is running inside, right? So that could be a performance bottleneck, this thing. On the other hand, if it's inbuilt operators, like a selection or projections or whatever it is, right? So those could go faster, right? So if you're writing your own flat map group with state with arbitrary code in it, right? Then we can't guarantee certain latency boundaries that you wanted to achieve because it involves a lot of your code. And the second one is when you have a Python, um, Python execution is a bit different. Python execution is essentially, I think, like before getting into all of them, should I go and explain about how the physical plan works in physical execution works in Spark structured streaming? Should I do that?
Just a second. What maybe it's easy to just draw like two VMs. So my understanding is this, that we have a JVM that talks to a Python interpreter, and that
Yes.
the communication is across a memory channel. Is that correct?
Yeah. So you have a JVM. Then there is a connection here. Then it has the Python process. So now data gets marshaled into this one side, get to the Python process, run your Python code. Then again it goes back. Data gets marshaled back again into JVM. Then it goes down to state updating or further processing downstream, right?
Yeah. So to be clear here, it's not shared memory. It is memory passing.
Yes.
And so the reason I make that distinction for those who may not understand the nuance of that question is the performance, that there is an inherent performance that everything is going to have to be marshaled and unmarshaled between these two processes. And there's an inherent overhead between that. And this is where we see some of the newer formats like Arrow trying to make it so that we don't pass memory. We have this other system to the side that's giving us memory access.
Yes, and it often the marshalling aspect is not the dominating cause. Because of the fact that the Python code has a GIL and all global interpreter lock and other things, right? So the Python code usually runs slower, even if you give a marshalling data very quickly, marshal data quickly, right?
Yeah. So it's definitely a consideration. If you're, what I've seen from the Pythonistas is that you scale horizontally, and that solves any of this. It is what it is. If you really want to do your data engineering in Python, I guess go for it. But my thought has always been your data scientists should be here in the Python, and your data engineers should be here in the JVM. But that's my strong opinion.
Yes. Yeah, I think we do a lot of uptake in Python because a lot of analysts who code, they do Python, and the performance is not their what is the biggest requirements, right? So they do a lot of Python streaming, and for them, a few seconds is good enough. In fact, some of the financial customers use Python heavily because they focused on development speed as compared to performance. They're okay with the 2 to 3 seconds.
Yeah, and I think that's really what's key here is if you have if you're doing an interactive system and 2 or 3 seconds where it's your data analyst or your data scientist here, hey, by all means, your trade-off of trying to get a data scientist or data analyst to learn Python or learn a JVM, probably not going to happen if they know Python. Just accept that. But if you're going to create high performance systems that are going to be consistently running, that's where I think, that's where I personally say, think twice. Maybe it should be in the JVM for several reasons, not just for the performance reasons.
Yep.
But that's me being a heavy Java proponent on this.
Yep. In fact, in any streaming system, the words of the hard way that I learned is what I call as a triangle. Throughput, latency, accuracy, or cost, or whatever it is. You can get 2 out of the 3, but not all 3. But I can't theoretically prove it, but it, what do you call it? It feels intuitive. So you choose which one you want to, which 2 is the paramount importance, so that you can optimize for that, rather than trying to optimize for all 3.
What was this one on the bottom right?
Accuracy.
Accuracy. Okay. I couldn't read your writing. I'm sorry. I wanted to make sure that people could read it, but this is accuracy right here.
My handwriting has gone bad after we started typing so much.
Now I see why you didn't want a whiteboard. Okay.
Yes.
So I would agree with you empirically on this of your chart. And normally in data engineering, you're trying to get a good metric or something as good as possible, usually trying to optimize for right there. And accuracy is left to a data system to hopefully be idempotent. But we'll see.
Yep.
So let's go to 5, and we've been talking and alluding to this, going through in depth about how the steps of a microbatch happen. Could you go through that for us?
Okay. So for each batch, I mean, in the Spark itself, there is a driver. Then there are executors. Executor 1, executor 2, three. And these executors are running on VMs. VM1, VM2, VM3. And the driver is running on another node, which is, we call it as a coordinated node or whatever you want to call it. And the executor has this notion of task slots. Task slot 1, task slot 2. And usually the task slot is equal to the number of cores. So now, once the physical plan is generated, so you plan the microbatch. So once the physical plan is generated, so now let's take the example of Kafka. Kafka has these partitions. Partition 1, running in a different nodes. Like three partitions.
This would be under a single topic. So this Kafka topic here is partitioned.
Yes. Yep. When a single topic partitioned into 4 different partitions, distributed across machines. Now, first thing that happens is batch planning. In batch planning, what you do is for each partition, I am going to, in P1 partition, I'm going from offset 1 to offset 2. On P2, offset 3 to offset 4. In P3, offset 5 to offset 6. P4, offset 7 to offset 7, 8, right? So like the batch is planned such a way, what offset in each partition that I want to take the data from and process that. And this data, what we call the batch planning, this data is persistent.
And to be clear, when you were given these offsets aren't incremental. That these offsets or whatever it last left off on. So although you put 1 to 2,
Yes.
normally that's 1,144 to 2,222. That this is just for ease.
Yes. Yep. So this is where the last point you left off, right?
And the one other thing is, to be clear, the timestamp of this and the timestamp of this is the amount of time for that microbatch. Likewise for all of these.
Amount of time for the microbatch means like processing time of the microbatch or waiting time for the microbatch.
Maybe that's a question to you. So is this I would assume that if your microbatch started at second 1000 and you had a microbatch time of 100 milliseconds, that it would be this microbatch here would be 1000 and this microbatch that offset here would be 1100. The timestamps of those. Well, the bounding timestamps. It is possible for it not to match up.
Yeah, it might not match up because remember, data is accumulating in Kafka, right? Your data is accumulating in the Kafka, and I am taking a certain amount of data out of it to process the microbatch. That can be controlled by the number of records that going into the microbatch, or how much amount of time that I have to wait before I start the microbatch. Okay.
So you could actually start. You could start before by time or earlier than that.
Yes. So you can say 100 records. So then each batch will have 100 records.
Oh, I see what you're saying. There's two ways you could do it: either record-based or time-based. Okay.
Yes. So then once the batch is planned, then the data is persisted. And the reason why we persist the data is in case if the batch failure happens, then when I come back and replay the batch, I know what offsets the data has to come from. And remember, this is deterministic. That's what we call as the batch stability. Okay. So this persistent provides batch stability. And this batch stability is very important when you do exactly once. I'll come to that later. So now, once the data is persisted, then the scheduler in the driver spawns out tasks. And the number of tasks is equivalent to the number of partitions in Kafka. Okay? So now, which means 4 tasks will be started. Task T1 will task at start task 1. T2 is going to be starting here. T3 will be starting here. And T4 will be starting here. Okay. So these executors execute the task for that microbatch. Once the task finishes, then we write another this thing. Once the task finishes, we call as done into a persisted log. So once the task is done, it's persisted, that indicating that microbatch is complete. So now you got the idea, like how. So now once that done is done, return, then next set of tasks is scheduled for the next microbatch.
And that was going to be my question. So the next set of tasks don't necessarily come to right here. It could be started over here and started over here. But tasks are assigned each microbatch.
Yes.
And this is something I find that people don't understand often when they're doing this, that they think that they can create a static variable that just remains here and gets used each time, and that isn't the way these distributed systems work.
Yes, you can't do that. In fact, like we are even making an optimization, which we call as microbatch pipelining, which is tending towards real continuous systems, but it's a hybrid of the two, where usually what happens is we wait until the microbatch finishes, until all the tasks, because remember we started 4 tasks here, right, for that microbatch, right? So we need to wait until all the 4 tasks finishes and write the persistent stuff before you start the next microbatch. So which means if task 1 finishes earlier, then that slot is being wasted, right? Because we can't schedule anything. So which leads to underutilization. So what we are doing at this point in time is we are doing something called microbatch pipelining, where the tasks of the next microbatch for microbatch 2, like T5, T6, T7, and T8 will be scheduled before the current microbatch is completed. So it means there is an overlapped execution of the microbatches. So that allows to heavy utilization of task slots that are available, and which increases the throughput. So we have, by doing this, we got a 3x increase in throughput and a 30% reduction in latency. That is going to roll out in next quarter. We already updated in our project Lightspeed update that this is going to come out. But first iteration is gone in. It's going to come out in Q3. Okay. This is a very exciting feature that we have been working on.
So unless you have anything else you want to talk about on these steps, we could talk more about the project Lightspeed. How does that sound?
Yes. But the thing is, do you have any questions before I go into Lightspeed?
I'm just looking this over. So so one of the things that you didn't talk about here was the actual data output over on this side. So let's say you had you were publishing back to Kafka. This is all done right here by this executor. So the publishing is done right then. Is that correct?
Yep. So the T4 task, which will directly publish into Kafka, whatever the output is going to be.
Okay.
And the key thing is in Delta, it's a bit different. When you're writing into Delta, when all the tasks finishes, we have the notion of a commit. Because Delta, we need to commit that microbatch, right? So that commit happens at a single point, which is the driver. When all the tasks of a microbatch finishes, commit goes to driver, and driver writes the commit log. So that way, what happens is, remember the batch stability that you made, right? So when you make the driver commit, it writes what batch ID that you have committed. So which means if that batch is getting replayed, we can retrieve that batch, what has been committed or not committed. So then you can clearly see, you can make it idempotent. If already that batch is committed, if you are reprocessing that batch, I don't know to commit that again because it's already committed, right? So which means that's what do you call a replayable source, an idempotent destination gives you a, what do you call exactly one system.
Yeah, let's get deeper into exactly once in a second because I do want to do that. But there was one thing I do remember on the driver. So as of now, the driver is a single point of failure in Spark. So if this dies, our streaming job dies. Has there been work that's gone into that?
Yeah, so we are looking at the fault tolerance mode of the drivers and everything. But the thing is, like, we are already saving enough state into the from the driver into S3, so that if we restart the driver, it can pick up the state from there. Actually,
yeah, it's more that to let people know that if you're going to have to do something, let's say Kubernetes or whatever, that makes sure that if this process dies, it gets restarted automatically.
Yeah, so and that aspect is there. The key thing is the state.
Yeah, your state. If this state to be clear, we're talking about state like this, these offsets. There's a lot of state, and then there's the state that may be coming out of the actual jobs themselves. All of that is important to keep track of.
Yep. So that is the thing. Like the driver restarts and everything is already available because we monitor the VMs because this driver is running on a VM too, right?
Yeah, I called it VM0. I added that for you.
VM0. Okay. So that one, like, so the VM0 and if there's a control plane that checks whether all the VMs are healthy or not. If not, it restarts the VM.
Yep. Okay. So let's talk about Lightspeed then, because much of this is very interesting, and so now it's going to become even faster. So let's go to 6 and talk about Project Lightspeed.
So the Project Lightspeed was conceived to advance Spark structured streaming. So advanced Spark structured streaming on multiple fronts. And the first front is performance. The second front is functionality. Third one is operations and observability. The fourth one is improving ecosystem. So the performance on our goal here is to increase throughput, lower latency, so towards this, we worked on a lot of projects and like microbatch pipelining. I'll explain some of the concepts here later, but let us see. We have been working on microbatch pipelining, then offset management. So microbatch pipelining gives 3x improvement in throughput. and a 30% reduction in latency. Offset management got stateless pipelines. Or sub-second. I think in the order of 500 millisecond latency. So what do you mean by a stateless pipeline? Stateless pipeline is essentially means you do take input, do some transformation like ETL or whatever it is, then spit output. You don't do any aggregation, join, or anything like that. So stateless pipeline is just grab data, do simple transformation. One example could be JSON. So JSON to XML conversion, or other way around, right?
I hope the other way around.
Yeah. So just the CPU cost and just conversion and putting it into another system or whatever you want to call it, right? So for stateless pipelines, going from Kafka to Kafka, we were able to do it under 500 milliseconds, 500, 600 milliseconds. So that is on the performance side, microbatch pipelining. Then we are also doing a lot of stateful pipelines. We are doing a lot of optimizations. What we call as a changelog checkpointing. Then some what do you call shuffle partitions affect latency. So especially when you have a stateful pipelines, we need to have some kind of a shuffle in the middle, right? So you usually have a task that writes into shuffle partitions, then another task reads from the shuffle partitions, like task 2 or task 1, and process it. And the choice of the shuffle partition influences latency. So this shuffle partitions, currently we are setting it to an arbitrary number of 200. And when it have 200, then 200 tasks are there. So 200 tasks we need to execute. Now, if you have around 10 slots, so which means you are going to execute only 10 tasks at a time. So which means first 10 tasks are executing, 190 tasks are waiting. But on the other hand, if it's like as I said in the previous example, there's only 4 tasks or 4 partition tasks that is executing, and if the shuffle partition is 4 tasks, then you don't have to wait. So in other words, the task of the shuffle partition task that we need to choose should be equivalent to the source task or the actual processing of the data in hand, rather than assigning an arbitrary number. So that is something that we need to work on. So these two, we found that reduces the latency by 3x. 3x low latency. So which means like we, on one of the stateless pipelines, we were around 6 seconds. We have brought it down to 1.25 seconds. So this reduced from 6 seconds to 1.25 seconds. That is a huge improvement that we have made.
It is, and that was, to be clear, that was no code change from the person or on their DAG. That was just Spark changes.
Yes, these are all Spark changes. No code changes, nothing.
Okay.
Okay.
For those listening, this is what you want. You want the work to be done in the framework to improve your code. Normally there isn't a lot of improvements you can make unless there perhaps some architectural changes that usually you want your framework doing this for you.
Yep. So that is on the performance side of things. We have more coming on the performance side of things. So then let me go into functionality. Okay, should I go to the next screen? Next.
Sure, you're running out of room. So yes, let's go to 7.
Yes. Functionality. Python arbitrary state processing. Arbitrary state. So one of the requests we had was in Scala, we have a flat map group with state and map group with state. So these APIs, what they do is give the user control over the state. So you can write your arbitrary code and manipulate state.
And arbitrarily manipulate state with whatever you want to store there.
Yep. Then after that, manipulate state and store the state. Okay. So that is the advantage in Scala, but there was no equivalent in Python. And that has been one of the asks for financial customers because they want to write in Python moving, what do you call, expected average moving, which is a popular function in what do you call in the finance world. So expected moving average or whatever it is called. I don't remember the exact. So everybody writes their own way of doing things, right? So how do you allow this processing to happen? So that is where we added the Python equivalent of the Python arbitrary state. And when this executes, you have the executor, you have the task slot. This is the task slot. The task is running here, which is a DVM task. Task slot 1, this is the task 1. And within the task 1, which is the thread inside the executor, so it will create a Python process. And marshal the data into the Python process and marshal the state also. Manipulate within the Python process and marshal it back. So that's why like the Python arbitrary stateful processing provides the flexibility. The framework handles all of them. Okay. So that way what happens is you can write your Python code, deploy it, and manipulate your state in Python, and you can have an end-to-end desired processing that you want in Python itself. This is one of the functionality. Okay.
Okay.
Any questions before I move on to the next one?
No, that seems straightforward.
Okay. So next functionality is multiple aggregate operators. or in fact, multiple stateful operators in a single pipeline. So usually what happens is, let us take the example of a chained aggregation. For example, you're having data source. You want to do a 10-minute aggregation window, right? Then you wanted to use that for 1 hour aggregation, and write into sync. Okay. And this was not possible because of the way the watermark was advancing. Because when the watermark calculation occurs at the end of the microbatch running the 10-minute aggregation, so it does not advance the watermark and the 1 hour aggregation. So which means the 1 hour aggregation was not computed correctly. So what we have done is improve upon it so that you can express this entire thing in single pipeline, and the results will be accurate. So essentially what we have done is the watermark propagation has been improved. So this allows a lot of set of pipelines. Usually these pipelines is broken into two. You do the DS 10-minute and write it into a data sync. Then read from the data sync, do the 1 hour aggregation, then write it into another sync. So this is not needed anymore.
Yeah, this is inefficient. I actually hit this in a project where we found out the hard way that this wasn't possible. So okay, good, excellent that we're fixing that.
Yep, it's already out. We fixed it and launched it in. I don't remember the DBR version, but we have all launched it already. So this is another major feature. And the third one that we are working on is improving state API. So this allows support for composite states. Like map, list, arrays. Which means in your state, you don't have to have a value as one single scalar value. You can have a complex value types, tuples, maps, lists, arrays, all the stuff. Then schema evolution of the state. Then third one is querying the state. So what happens is you have a pipeline using data source, pipeline, it's writing into state. Sync. So now for debugging purposes, user would like to query the state, right? And so this, so we are working on a Spark source connector to read the state. So once you write a Spark source connector, we can write a Spark program to read it. Now we're also looking to move the state into what do you call it? Delta. Right? And then use the DB SQL. So essentially, like what happens is once the pipeline starts running and the state cards are accumulating, you can do a SQL to type the query and get the state completely. So that way, your debugging becomes simpler, right? And eventually, you can even serve out of the state also.
Those are all good.
So these are advanced functions. Yep.
So just to help people understand, this composite state, this one, it's you'd either have to put your own object in there. That was a map, and then but ideally it would be a map there, because if you're going to query it over here, you need to know it's a map or it's a list or what have you. The schema evolution here is really important. Although you kind of skipped over it, this is one of the biggest pain points that people will have, where if you have some state here and you go from V1 to V2, that can be a huge issue between the two. And if you can't, if you didn't think about your schema evolution in V1, your V2 will be much more difficult. And then this querying the state, this is often what people are wanting to do. What is happening now? What has happened over the past few minutes? This is all very helpful in terms of looking at that.
Yep, this is all coming out in another 6 months or so. But essentially, as you can see, we have improved the state manipulation completely to what do you call match the functionality. And since we have a Delta or Lakehouse, and Lakehouse has all the query capabilities, we are essentially tightening the integration. With the tightening of the integration, we can even one of the other thing that we are doing is catalog integration, QC catalog, so that you can look at the tables, streams, and the schemas, and provide data lineage. Data lineage and data governance. So these are all functionalities that is rolling over.
Excellent. I'm excited about those features.
Yep. So this is on the functionality side, and
you have the two, the operations and the operations and observability, and then the improving the ecosystem.
Yep. Let me do that. On the operations side, first thing is viewing of the DAG and more metrics. Currently, we have a minimal metrics. Now, more metrics have been already available, but it's a question of dashboarding it. And visualizing it. So dashboarding it and visualizing it are the two aspects in more metrics and this thing. And streamline log access and pinpointing the errors. And exporting metrics to different systems. different systems means Datadog, and cloud providers, AWS CloudWatch, and Google GCP monitoring, etc. So these are the various things on operations. So now, as you know, like our DLT, which is actually like the Spark streaming running on the operation side of thing with operation capability, already provide auto scaling. DLT is essentially like nothing but a Spark structured streaming running in the with the fully operationally managed. So you fire it and forget it. That is the concept. So it will do auto scaling. It will create cluster, launch cluster, auto scale, restart if any issues. All these operation stuff is automatically taken care of for you. So you can write in DLT Python as well as SQL, fire the query, and the cluster is automatically created, launched, then processing start automatically happen. If there is a need for auto scaling, it will scale it up the cluster and scale it down during downtime, and restart it if there is an issue, and also software update automatically does. So that way, what happens is, in a sense, it is on the what do you call the Google data flow kind of aspect where we can do all the management automatically without the user intervention. So that way, the key is of the DLT is to take streaming to the masses. So analysts who can write Python, who can write SQL, can drop it without having to worry about all the data engineering aspects of it. So that taking the mainstream streaming to mainstream.
Makes sense. And if somebody else is handling the ops side for that, then if they blow it up, then it becomes a cost function rather than a downtime function.
Yes. Then on the ecosystem, we added more connectors. So we are adding Pulsar connector with supported, inbuilt support. Then we added a PubSub connector.
That's the GCP PubSub, correct?
Yep. And the PubSub is challenging. The reason why it is challenging is PubSub is not a true stream messaging system. It's kind of a queuing, kind of a masquerading where sometimes message will be delivered, re-delivered, even if you acknowledge it. So it's not a clear semantic. So essentially what we have to do is we have to, there's no notion of replaying and everything. There's only one message ID. You can't replay from a certain offset and replay it. You can't do that. So it complicated the thing. So what happens is we do something called a prefetching, or rather fetching, not prefetching. Fetching data and deduping it. So essentially, there are two steps that happen deduping data before we let the data in to be processed by the structure streaming. So essentially, we fetch the data, write it into our delta for deduping purposes, then this thing. So pub/sub fetch data, dedupe data, then Spark structured streaming pipeline, then sync. So this provides exactly one semantics. So then we are working on a lot of CDC connectors. So that you can get the data, dump it into S3, and put that into analytical data warehousing. So this on the improving on the ecosystem. We added IAM support for Kinesis, and also about EFO support also. You know EFO support? The EFO support is actually like there was only 2 MB of bandwidth shared by all the consumers.
Yes.
Whereas
Yeah,
EFO
it's a major
is 2 MB.
limitation of Kinesis.
Yep, dedicated now for every consumer. And up to 10 consumers, you can do it. So that's all about Project Lightspeed. So there are some of the things, there's still a long way to go in terms of another year and a half worth of we are doing. But it's all improving the Spark structure streaming by, so already it has improved quite a lot, and you can confidently pick up Spark structure streaming and use it. There is a lot of investment going into the Spark structure streaming to make it much better, and probably the best streaming engine in the from all different viewpoints.
That, as we were talking about before, that's the goal. The goal is to have one system to rule them all. That you don't have to have several different processing systems. So I have one final question for you, Karthik. Why do you think streaming is important?
Streaming is important from an enterprise point of view.
Any point of view.
Okay. I mean, from an enterprise point of view, the reason why streaming is important is because of the fact it gives insights quickly. And I mean, I typically divide them into 3 different workloads. So one is the ingestion workloads. Analytical workloads, operational workloads. So operational workloads essentially means, are you able to see it? I've already drawn it, but it's not showing up on the...
Yeah, it'll take a second. So that's probably Google pub/sub behind the scenes taking too long. I'm not sure how they... I'm not sure how they did Jamboard. That's what we're using for this. But every so often, there's just this latency jump that's really odd, and I never have figured out what it is. Yeah, let me see if I can get it to refresh. Oh, that's because
Okay.
I was on 12 and you were on 13. There we go.
Oh, okay, 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 okay.
Okay,
Uh,
so we've got
so
ingestion,
we,
analytical, and operational workloads.
yep. So the operational workloads are usually continuously on. The sense like when simple examples being when elevator button needs to be modified, continuously monitored, and if there is anything that comes through, you have to um, some alerts and everything, monitoring the elevator. Some threshold conditions met, you have to alert a business process. That is operational workloads. And these are all very important business problem because it's tend to business operation. And the more latency sensitive it is, the better the outcome is from a business point of view because you get to the service quality of the business quickly enough, right? And analytical is for visibility purposes. Real-time analytics is for visibility purposes, and that is very useful for lot of things like ad targeting and etc., right? So, I take the example of Twitter, where ad targeting is very important in the presence of Super Bowl. So, because Super Bowl has a certain window, we need to quickly analyze which ad is working, which ad is not working, and put more money behind this ad. These decisions have to be made in real time, and that's a classic example of how the analytics is driving decision making in an instant fashion or even in an automated fashion. And these two workloads cannot be powered unless the ingestion is in real time, right? Ingestion also is a particular set of workload which is continuously ingesting data from the different data sources, right? And all of these things, in order to get timely visibility and insights and timely decision making, streaming is essentially important for enterprise. Every enterprise should, if they are not looking into streaming, they should better get into it because the competition is always looking into it or already they are put in production. Today, Databricks has more than 3,000 or 4,000 customers doing streaming. This is a lot. And we are in the process of growing.
Well, good. So, as I think you made a very poignant point here, ingestion. Sometimes people, will, especially with the whole generative AI, they're just always
Uh-huh.
trying to skip to this analytical workload and say, let's just put some machine learning up in production and they
Yes.
forget, well, what do we run that on? We need this ingestion, and this ingestion will power our operational workloads, our analytical workloads. And so,
Yes.
yes, we want this, but we need this. So it's almost as if we should draw some lines in
Yes.
there of relationships. Well, good.
Yep.
Uh,
And ingestion is one that powers because without ingestion, you cannot feed data into models or everything for decision making, right? And the more the latest the data is, the better it is.
yes, yeah, we're reacting, and I think that's the key
Yes.
here is if you need to react fast, reacting fast is
Mm-hmm.
that's what real time gives you. If you don't have real time, you can't react
Yes.
fast. So
Yes.
excellent, Karthik. I appreciate it so much. So. I guess that brings us to the end. This was very in depth. We went really deep into Spark streaming, and I appreciate it so much. If you're watching this and you're thinking, "Hey, I need some help with Spark streaming," you obviously have Databricks, and you have my company that can help you on that. And with that, thank you again so much for being here. I really appreciate it, Karthik.
Thanks for having the opportunity, JC. It was a pleasure.